let's think about halogenoalkanes. This is usually one of the first mechanisms that you're introduced to in A-level, and mechanisms can feel a little bit scary. Actually, hopefully, when you go back and look at your free radical substitution mechanism, which is what we're going to look at now, you realize actually they're not that scary. If you do find it scary, I would highly encourage you to spend a little bit more time actually thinking about the mechanism that happens here. So you don't have to be able to do the mechanism. You don't need curly arrows, but I probably will do a couple of curly arrows to help with understanding. You do have to do a curly arrow, sorry, to show homolytic fission, which we'll come to in a minute, but you don't have to do what we're going to call a proper mechanism here. But if you do find it hard to understand and get your head around free radical substitution, I would highly recommend you actually think about the actual mechanism, because it makes it a lot easier to fit the puzzle pieces together. But we're not going to think about it too much now, unfortunately, because we don't have time. So let's just think about what we need to know. What do we need to know? We have to know that there are 3 steps in free radical substitution. The first step happens when there is the presence of UV light. So if we have halogen or molecular halogen and the presence of UV light or a high temperature, then we can undergo free radical substitution, because the first step can happen. And that first step is called initiation. It's the formation of a radical. What is a radical? A radical is a species with an unpaired electron. Why is that important? It's a stable species with an unpaired electron, I should say. Stable, because it can exist. Not stable because it's unreactive. It's not unreactive. They're very reactive. Radicals are very reactive. They are also, just as a common issue, they are also neutral. So a common thing that we think about when we draw, for example, a chlorine radical, is you think, well, because it's got an electron that's on its own, it must have a negative charge. It doesn't. They're neutral, because a chlorine atom with an unpaired electron, because it's got 7 electrons in its outer shell, so one of them is unpaired, has got, how many has chlorine got? 17 electrons, 17 protons. So it's a neutral species. A chlorine atom is neutral. We just rarely see radicals because you have to have that extra energy present in order for them to exist as their very reactive, unstable radical in their radical form. Otherwise, chlorine would be bonded. It would be an ion, so it would have gained an electron to make it stable, or it would be bonded in a covalent bond, so it would also be more stable because it's sharing that extra electron. Radicals exist because we've given those species a little bit of extra energy so they can exist in their high energy, unstable states. But that doesn't mean that they've got an extra charge. It's the same thing. It's an atom, but that is allowed to exist with an unpaired electron. So initiation happens when we form a radical. We'll look at this. We're looking at an example of initiation in a minute. But one of the ways that I kind of help students to remember the difference between initiation, propagation, and termination is, what does an initiation step have to look like? It has to start with what I'm going to call a normal species. So a bonded molecule, compound, whatever it is. It has to start with a normal species and form 2 radical species. If it does that, it's initiation. It's creating at least 1 radical. You can't start with no radicals and not create 2 because of the way that homolytic fission happens. But we have to form a radical in initiation from no radical. The next step is propagation. Propagation is continuing radical formation. So it's taking a radical, reacting it with something to create a radical and something else. So propagation steps must start with a normal species and a radical species and create a normal species and a radical species. If somehow your propagation step has combined 2 radicals to make a normal species, that's not propagation. If somehow your propagation step hasn't created another radical, it's not propagation. The word propagation means continue. So we have to continue with our radical species. You must create another radical species out of your propagation step. Make sure that your radical is regenerated. And then also a termination step or termination steps. This is where we start with 2 radicals and we create a normal species. 2 radicals collide to form a stable product. The stable product must have no unpaired electrons. So no radicals in the product of a termination step. Again, it's terminating, it's finishing this free radical substitution mechanism. So we've got to get rid of all the radicals. Technically, radical substitution can continue until all of the hydrogen atoms in an alkane have been replaced. So substitution, we're substituting the hydrogens in an alkane for halogens. That's how our free radical substitution, that's what the substitution does. So technically, it can happen until all of the hydrogens are replaced. Usually, though, we only look at the mechanism for the replacing or the substitution of a single hydrogen. But be careful, because they can ask you to replace or substitute the second hydrogen or the third hydrogen or even the fourth hydrogen. So be aware that you could be expected to do all of them. We're only going to look in detail at one, replacing the first one. This can only happen if conditions are maintained. So if you've got your, enough of your radical species, and if you've kept the light, UV light and or high temperature present. So if conditions are maintained, i.e. UV light or our high temperature, so usually around 300 degrees C. Radical substitution is also unpredictable. And again, one of the things we're not going to focus on too much, but that you do need to be aware of, is that you can create a mixture of products. We've called them side products here, but actually they're just products, because we can talk about what we would class as our usual initiation, propagation, and termination steps. But what if those species don't end up reacting? What if you get to other radicals reacting? You might create a product in a termination step, which is not what you were expecting or not what you were going for. So we can create lots of side products in our radical substitution reaction. So let's think about some reactions. We'll go through it nice and speedily, just so that we don't spend too much time on this. But we've got initiation step, propagation step, and termination step. Let's work. I'm just going to go as basic as possible. But bear in mind, obviously, you might be expected to do things that are a little bit more complicated. Not too much more complicated, thank goodness, but a little bit more. So initiation, let's start with our chlorine. So I'm going to do chlorine, the substitution, free radical substitution of chlorine with methane. So we've got Cl2 and we've got our UV light. What is going to happen? What is going to happen? We'll think about the mechanism in a little bit more detail on the next slide. But what is going to happen? We're going to get the formation. It's an initiation step, so we've got to form a radical. In this case, we have to form 2 radicals because we're undergoing homolytic fission, so we must form 2 radicals. Now, you will always be expected, no, let me rephrase that. There are always 2 propagation steps to get to the product that you're aiming for. There's always 2. You might only be asked to give 1, or you might be asked to give the second propagation step or the first propagation step or something like that. But there are 2. There are always 2. The first step in the propagation steps is preparing your radical for the second step, which produces the product that you're aiming for. And I'm using quotations because you might be asked to be writing the propagation steps to form an unwanted side product or something. So the thing that you're aiming for is produced in the second step. So the first propagation step starts with your alkane. And I'm going to draw it like this to try and make it a little bit easier to see. But this is methane. So I've just drawn in one of the hydrogen carbon bonds, just to kind of highlight that that's what's going to be broken. That's my normal species. So I also must have it reacting with a radical. That's my normal species. You're then going to form, or you're going to break this carbon-hydrogen bond using homolytic fission. So they're going to separate. You're going to take 1 electron each, and that means we're going to end up with a methane radical, and sorry, that's a rubbish dot, a methane radical and HCl, because the chlorine radical is reacting or stealing away the hydrogen and its electron to form a covalent bond and leaving your methane radical or CH3 radical. So we've prepared our radical. Notice we've got a normal species and a radical going to make a normal species and a radical. I'll also just make a quick note. It doesn't matter massively where you put your radical dot. If it is a radical, you must put your dot because you need to tell other chemists that you know that that species has not made all of its bonds or has not reacted to form an ion, and that is on purpose. So we must make sure we draw the dot that represents it as a radical. That is our unpaired electron on its own. But it doesn't matter where you put it. You could put it, so for example, I could put my chlorine radical on the left-hand side, or I could put it on the right-hand side. Just if I were you, I'd try to be consistent between elements so that your examiner isn't confused. And personally, I find it easier to understand and remember if I draw the dot next to the species that is carrying the radical. Not always easy to do, but that's what helps me to think through the process and to think about the mechanism. But it doesn't matter if some are on the right and some are on the left, as long as you try and keep the radical as close to the species that's carrying it, then that's fine. And you haven't drawn 2 or on 1 species or anything like that. Okay, second propagation step takes the radical that we've just prepared, and we're aiming for a product. But what do we react with? What is there lots of hanging around that is able to be reacted with and that is going to help us produce a radical that can propagate afterwards? Well, it's got to be something that can help us produce another chlorine radical. So it's got to be a Cl2. And there's lots of it around. We know there is because we started with it to begin with. That means we're going to end up forming a chlorine carbon bond. And because we've broken the chlorine-chlorine bond, we end up with a chlorine radical. Again, we started with a radical in a normal species and we ended with a radical in a normal species. We have propagated the free radical substitution. And finally, termination. Now, there's normally, when you're asked to give a termination step, have a look at the specifics. Often they will specify which termination step they want you to give, so just be careful. I'm going to give all 3 that are currently possible within our setup, but of course, if you've got side product, if you've got further substitutions happening, there could be loads of different propagation and termination steps that you could be asked to give. So just read the question really carefully and check what it is they're expecting from you to make sure that you give them the answer that they want. But there could be, in this case, 3 different termination steps. How can we get 3 different ones? Well, there's termination step, which is just the reverse of initiation. So that's kind of the easiest for me anyway to remember. It's just the reverse of initiation. 2 chlorine radicals forming a normal species, that's termination. 2 radicals form a normal species. But what if we look, we've actually got a CH3 radical floating around as well. Now, the chances of these radicals colliding is very low, which is why free radical substitution is such a horrible reaction, because the chance of a termination step happening is very low. But it is still possible that, for example, 2 chlorine radicals will collide. It's also possible that 2 of our methane radicals would collide. So what would we form then? We'd form a C2H6 molecule, where you could write it as CH3CH3 if you wanted to. But you will have formed ethane if those 2 collide. Or maybe, again, it's going to be very unlikely to happen, but it is still possible. So it could be one of the products, could cause one of the products. What happens if your methane radical combines with your chlorine radical? Well, then look, we make our product that we wanted again, or that we were aiming for above. So all of it is very unlikely that they will happen. It's unlikely that termination steps actually happen at all, because the likelihood of 2 chlorine radicals combining is very low, or 2 radicals, meeting is very low, because they're not going to be very concentrated, but it is possible. So those are 3 possible termination steps here. Okay, let's whiz on. So you don't need to know the curly arrow mechanisms for initiation, propagation, and termination. Sorry, for propagation and termination, but you do need to know it for the initiation step, because we need to talk about fission, specifically homolytic fission. So if your covalent bond fission is the breaking of a covalent bond, we can have homolytic fission or heterolytic fission. Homolytic fission is when both atoms in the bond receive one electron from the bond pair, and homo meaning same, same splitting. So lytic or lysis is splitting. So homolytic means splitting similarly. So both species receive an electron. We create two species that are the same type of species, so two radicals. For example, let's have a look at, let's do it with chlorine because that's one of the most common ones. In the presence of UV light, we create our two chlorine radicals. So how does that happen? There are two electrons in the chlorine-chlorine bond. Each chlorine has obviously got 3 lone pairs as well, but the shared pair of electrons involved in that bond is shared between the two chlorines, and one electron goes back to one chlorine, the other electron goes back to the other, and that's why I've kind of drawn a half-headed arrow. And it's a point of contention for me because lots of people call that a single-headed arrow. Lots of people call it half-headed arrow, or, you know, half an arrow or whatever. And so it's confusion between double-headed arrows which point in both directions, or a double-headed arrow that's got both its bits to it. It's a confusion. Just be sure you know what I'm going to call single-headed arrow looks like. Okay, it's only got a single side to it, and that's representing the movement of one electron. A double-headed arrow, or an arrow with both bits to the point, is representing the movement of 2 electrons. So specifically, it's the movement of 1 electron. That's with homolytic fission. With heterolytic fission, one atom in the bond receives both electrons from the bond pair. And this is what we're used to when we talk about bond fission, when we talk about breaking covalent bonds, because usually we're looking at the resulting formation of an ion. So if we've got, let's just do a halogenoalkane. Heterolytic fission often comes from when we've got a polar bond, because we've already got partial splitting of that bond. The electrons are already spending most of their time around one of the species, in this case the bromine, the more electronegative species. And so both electrons, the pair of electrons, will end up moving over to the bromine. That means we end up with a species with the opposite charge. We've got a CH3 plus and a Br minus. So hetero meaning opposite or different, charged species at the end. You do need to be able to show what they're called, arrows, curly arrows for heterolytic and homolytic fission, with an example that you would be given in the exam. The reverse of either, hopefully we're clear, is called covalent bond formation. So either with 1 electron coming from each, or 2 electrons coming from somewhere, doesn't matter. In both cases, we are forming a covalent bond. So that's the reverse process. Okay, let's have a quick go at this one. I'm not going to give you too much time to do it because I'm very aware that I could easily run out of time going through all of this stuff. But bromine and ethane are heated together under UV light to produce C2H5Br. Name the reaction mechanism and state 3 examples of unwanted side products that may be produced. We're assuming here that unwanted side products is not what we would consider to be the main product. Or if this was free radical substitution to produce a halogenoalkane, that singly substituted halogenoalkane is the wanted side product. So anything else would be unwanted. Suggest how these products may be separated or could be separated. So context. Looking at what I've got an alkene. So I've got an alkane and a halogen. So my context is reactions between alkanes and halogens under UV light. Now that's the nice little flag for me, because that is the thing that makes me go, oh, free radical substitution, UV light. So that's my context. The command word is name. So I need to give a name of the reaction mechanism. So short answer, and then a state. I need to state, so again, short answers, 3 examples of side products. But then I also need to suggest how these products might be separated. So I also need to give an example of how they might be separated. Again, this is a suggest question because this is not specific recall knowledge that I've been given in my exam, in my specification. I haven't been told specifically to know how to separate unwanted side products in this specific reaction. Therefore, I can take comfort in the fact that this isn't something I should be able to recall. It's something I should be able to work out. So name and then suggest. And state as well, really. And then direction, consider unwanted side products and separation. So I've been directed to think about the unwanted side products and then how I can separate those. So what would you say if this was you? Bromine and ethane are heated together under UV light to produce C2H5Br. So that's our wanted product. Name the reaction mechanism. Well, UV light, my head says free radical substitution. So that's my free radical substitution. Just check my spelling. That's my reaction mechanism. Give 3 examples of unwanted products that might be produced. Well, I'm undergoing substitution from C2H5 Br. So from C2H6 to C2H5Br. So what else could happen? What other products could be produced? If they'd specified in the termination step, that might have given me a little bit more guidance, because the termination step involves radicals. So that's what I'm going to use, because that is very easy for me, therefore, to see side products. So what the radicals that are going to be present? The radicals that are going to be present are bromine radicals. So if 2 of those were to combine, we would end up with Br2. That's unwanted because we're trying to produce C2H5Br. So Br2 is going to be unwanted. What's the alkane radical that's going to form? Well, if it's coming from C2, it's coming from ethane, so C2H6, it will be C2H5 radical once we've removed one of the hydrogens. So if I have 2 of those, that's going to produce an unwanted side product that's C4H10. Or you could write the full, what's it called? The structural formula for it as well, if you wanted. So C4H10, that's another unwanted side product. Or what else? Technically, you could have a further substitution. So something, so Br2, C4H10, those are my 2 unwanted side products. I've given the equations to kind of help us understand it. They haven't asked for it. So they've just asked for the unwanted products. So that's that one and that one. And then what about if I had a double substitution, C2H4Br2? That's also an unwanted side product that could be formed. There are quite a few answers you could have given here. That's just an example of some of them. How would I separate these? Well, how can you separate species that have that are all similar but not the same? What examples of separation techniques do we know that would work here? So there's a couple you could give. You could talk about chromatography. If you've learned about chromatography already, then you can separate via column chromatography or gas chromatography. These are probably gases, so gas chromatography. If some of these are liquids, so bromine would be a liquid, it'd be easy to turn it to a gas, but it is a liquid, so you could also use fractional distillation to distill off some of these. Again, actually, butane's still a gas, isn't it? Yeah. So if we cooled it down enough, we could use fractional distillation. That would work, or a separating funnel as well. If you've got liquids, you could use a separating funnel. That would be a liquid. I'm pretty sure butane is a liquid. So C2H, no, butane is still a gas. So again, we'd have to cool it, but we could cool it down and then use the separating funnel. That would be fine. Okay, how are we doing for time? Fine, let's keep going. So that's 5 marks, 1 for the mechanism, 1 each for an unwanted side product, and 1 for your separation technique.